Hey physicists, today we're going to talk about geometric optics, particularly lenses. So if you remember in the last video, we talked about mirrors. Well, today we're going to talk about a small subset of lenses. So if you remember that rays from a very distant source come in parallel. So for instance, if I take the sun is giving off all this sun rays and those waves are heading towards the earth. But because they're coming from so far away, by the time we get them here, they are fairly parallel. Now, the same thing happens if we're dealing with the light in the room, but this is just a great way to show that example. So when we talk about thin lenses, then we're going to talk about two types of lenses specifically. The first one is going to be a converging or a double convex lens. And the reason it's called a converging lens is because it converges the light together on the other side of the lens. So here's my lens. You can see already why it might be also called a double convex lens, because it has that bowed out look on both sides. If we only have one of those bowed out and the other side is flat, we would call that a planar convex or convex planar lens. Because planar being that flat line. But as we look at it, it has this two focal points, and if these parallel rays are coming in, like we said earlier, it focuses them through the focal point, and that's why it's called a converging. It converges all of those rays into that focal point. Here's an example of one that's a real one. So here's an image where we have these light rays coming in and they get focused all the way over here to the focal point from that. The other type of lens that we're going to talk about is a diverging lens or a double concave lens. So you can already get a sense of what that's going to look like if I'm talking double concave. And what it does is it spreads the light out. So see how these are bowed in or concaved. And I have my line down the middle. I have the two focal points, and I have these parallel rays that are coming in, and notice that they get spread out or diverged away from this focal point that's on the left side of the lens there. Here's an example of that you can see. Here's a lens, and the light is coming in this way, and it's being diverged away from that focal point, which is all the way over on that left side. So one of the things to note then is that each of these lenses has two focal points, one on each side of the lens. So those two focal points are going to become very important. We have a focal point on the right side, a focal point on the left side of the lens. Now, back to our rules. When we're drawing these rays that we talk about, you'll notice that the ray rules are very much the same. The first ray is going to be parallel, and then it's going to go through a focal point. The second ray is going to be through a focal point, and then it's going to go parallel. And the third ray, instead of going through the center of curvature, it's going to go through the center of the lens. Okay, so parallel focal, focal parallel, center of the lens. Now, each rule is almost the same, so we just talked about the difference of those, but what's really, really important is to remember that each focal point is only used once. Each focal point is only used once. Each focal point is only used once. That's one of the biggest mistakes that students have as they're drawing these out. Now, when we talk real or virtual, upright or inverted, larger or smaller, all of those are the same as before. It's real if the actual refracted rays hit the image. It's virtual if we have to draw dotted lines back to get an image from that. Upright if it's upright, inverted if it's upside down, larger if it's bigger than the original, smaller if it's smaller than the original. Okay, so those are all the same as before. So here we have our converging lens or a double convex. So if we draw our first ray, remember it goes parallel to the axis and through the focal point. So the first thing we're going to do is go parallel to the axis. Now the question is, which focal point do we go through? And this is where it becomes important that we know what kind of lens we're talking about. Because this is a converging lens, it's going to pull all of the rays together to this focal point that's on the right. So since I went parallel to that, I'm going to come down through and go through that focal point. Now, the second ray, remember, it goes through the focal point and then goes parallel to the axis. So because I've already used this right focal point now, I have to use the left focal point this time. So I'm going to come down through that focal point. Once I hit the center of the lens, then I'm going to go parallel, and you can already see over here where that image is going to show up. And remember, we just draw the third one just to verify or to confirm that we drew the other two correctly. We didn't necessarily need to do that with mirrors, but it really, really helps, especially with the lenses where we're only using one focal point, because if you mess up on that, then you'll look at that and be like, oh, I see these aren't meeting where they should. And that third ray helps. So remember that this one goes through the center of the lens. So we're going to have a line that comes down through the center. Again, it meets over there, and that's where our image is going to be. Now, is it real or virtual? Do the actual refracted rays touch the image? Yes, they do. We have all our solid lines over here touching the image, so that's got to be a real image. Is it upright or inverted? It is going to be upside down, which means that it's inverted. And is it larger or smaller than the original? And for that, I can easily just look at, like, is this height compared to this height? And it looks to me like that's going to be a smaller image. So a diverging lens then, so the first thing I'm going to do is I'm going to draw this arrow that goes straight down the center of the lens there. And the first ray that I'm going to draw then, remember that it's going to go parallel to the axis and then through a focal point. So it'll go parallel to the axis. But remember that a diverging lens, it pushes away from this focal on the right or away from this focal on the left. So I'm going to have a ray that goes up that way in that direction. Remember, the next one then is that it goes towards a focal point and then parallel to the axis. Well, since I already used this left focal point, I can't go towards it. I have to go towards the other focal point, but as soon as I hit the center of the lens, then it gets refracted and it will go parallel to that. Now, remember, our third one is what? It's going to be through the center of the lens. So I'm going to have a line that goes down through the center of the lens. Now, when you look at these three refracted rays over here, where do these three rays meet? Do they meet over on the right side of the lens? And the answer is no, which means I have to draw dotted lines back over here onto the left side of the lens. So I'm going to extend my blue line back. I'm going to extend this purple line back. And notice that I have this point right here where all three of those meet. And because I have dotted lines there, is this a real or a virtual image? Virtual, because of the dotted lines. Is it an upright or an inverted image? It's upright. It's going upwards. It's not upside down. And then is it larger or smaller? And you can clearly see that this is smaller than the original one there. Okay. Now, the equations are the exact same equations. So we still have our HIHO negative dido equation as our magnification equation, and we still have our lens equation that's the 1 over f, 1 over di, 1 over do. The thing that changes on this is the sign convention. So we're still going to say if it's upright, then it's going to have a positive height. And if it's upside down, it's going to have a negative height. What changes now is when we talk about our signs, and this will make a little more sense when we talk, since we talked about lenses too, is our signs are really going to be positive if it's on the side where it should be. So since my image is on the left side and I'm looking at it from the right side, if my image, or I'm sorry, my object, since my object is on the left side and I'm looking at it from the right side, if my object is where it should be, then that DO is going to be positive. If my image is where my eye is, because that's really what I want to see, then I'm going to have a DI that's positive on this side. Same thing happens with the focal points. If the focal point is on the same side as my eye, it's going to be positive. If the focal point is on the side that it shouldn't be, where my eye isn't, then it's going to be negative. And if the image shows up on the side that it shouldn't be, it's going to be negative. So that's sort of the logic behind why the signs are what they are. So when we talk about this, we're going to say our DO is positive if it's over here on the other side of the lens where it should be, like I'm looking through the lens, and it's negative if I'm going to put my object over on this side where my eyeball is, which is kind of like, well, why would I look at something through a lens with it on the same side as my eye? That doesn't make sense. Then my DI is I really want that image to show up over here where my eye is. So that's why behind the lens or where my eye is, it's going to be positive, and then it's going to be negative if it shows up on the wrong side of the lens. And then for converging lenses, because it's the side of my eye, that's going to be positive F. And for diverging lenses, it's going to be negative. Now, remember in the problems, they're not going to tell you the positive and negative parts of that. You're going to have to know that sign convention and make the values negative when you plug those into the equations. Particularly, diverging lenses negative F and converging lenses positive F. So speaking of, let's do a sample problem here. With a converging or a convex lens has a focal length of 31 centimeters. So I know that this F value is going to be 31. I know that this 2F is going to be 62. Now remember, the 2F is just a reference point, same as the center of curvature was just a reference point whenever we were talking about mirrors. Okay, so I have this object and it says that it has a height of 11, so the height object of 11 centimeters. and it's placed a distance of 45. So notice that it's over here. This was 31, so we went over about another 10, and that's going to be 45 there. So we want to first draw our ray diagram. So remember, our first ray is going to go parallel focal. So I'm going to go parallel. And then which focal point do I use? Do I go away or towards the left focal, or do I go away or towards the right focal? And remember, that depends on what kind of lens we're looking at. So since this is a converging lens, it's going to converge it through the right focal point. So I'm going to come down through that focal point. Because I use that focal point, I'm not going to use it again for the second one, which means that if I have the next rule, which is through the focal and then parallel, I'm going to have to come down through that focal point, and then I'm going to go parallel to that, and we can already see that the image is going to meet somewhere over here. And just for kicks and giggles, we draw our third one, which is going to be through the center of the lens, and it meets down there also. So notice that our image, it's going to be a really big upside down image, right? So if we go to, let's talk real or virtual. Got to be real. And why? Because the actual refracted rays are hitting where the image is. Is it upright or inverted? It's got to be inverted because the image is upside down. It's on the negative y-axis. And is it larger or smaller than the original? And I hope you unanimously say that it's larger because it is taller in the negative direction than the object is in the positive direction. So now let's do some math here. The image produced will be so many centimeters from the lens. So in this case, it looks like we are looking for the we're looking for the DI, right? We're looking for DI. What's the image distance? So since I know my F, and I know I'm looking for DI, and I know my DO, isn't that going to be this 45 centimeters here? So since I know those, I'm going to use my 1 over di, 1 over do equals 1 over f. So I put in the 45 for my do, put in the 31 for my di. Now, big question. Is the focal length of a converging lens positive or negative? And if you think through, like if our eye is over on this side, is the focal point where it should be on the same side as my eye? The answer is yes. So this is a positive focal point. So in the equation there, it's correct. And when I solve that, I'm going to do 31. So if you're punching this in your calculator, it might help to say I'm going to do 31 x to the negative 1 button minus 45, and then hit that x to the negative 1 button, and I'm going to get an answer. Then I'm going to take my answer and do that x to the negative 1 button one more time. So remember, I have to do that one last time. Sometimes you'll see this x to the negative 1 button as a 1 over x button, for those of you who have a different kind of calculator. And for some of you, it's easier to think that I'm literally taking like 1 over 31 minus 1 over 45. Like that's sort of the math that's going in behind that, and that will give me my DI value. Okay, all that to say, I get an answer of 99.6 centimeters. And does this look like it is roughly out 100 centimeters? Yes, it's way out beyond that 62 centimeter mark, and that could easily be 100 centimeters, okay? Next thing, the magnification of the object is going to be something times, like how big is that going to be? So it looks like I'm looking for M again. So I'm going to do the hi-ho dido, hi-ho negative dido, and I know my DI, I know my DO, so I'm going to put in a negative 99.6 over 25, and I get negative 4 is my magnification. Now remember, what does that negative tell you? It tells you that it's inverted, it's upside down, and my image actually shows that it's inverted there. Then what does the 4 tell you? It tells you that it is, if I look back up on the question here, it is 4 times bigger than the original object, and you can literally see that there is that big size difference that's there. Lastly, if I'm looking for the height of the image, I'm going to use the exact same equation, that m equals hi-ho part of it. So I have the negative 3.98. I can plug in my hi and then plug in my ho, which is 11, and solve and get the actual height of it is that 43.8 centimeters. So that is a converging lens problem. Moving on, a diverging lens problem has a diverging lens has a focal length of 25 centimeters, and an 8 centimeter object is placed at a distance from 40 centimeters of this object. So it looks like this has a 25 centimeter focal length. This would be then 2f would be 50. This was placed out here at 40 centimeters, which is going to be my DO, and my height of the object is going to be 8 centimeters, right? So ray diagrams. The first ray goes parallel and then through a focal point. And what does a diverging lens do? It pushes it away from this left focal point. So that's why this one goes up that way instead of down through the right focal point. Secondly, goes through the second focal length. So remember, I'm not going to use this left one now because I already used it. So I'm going to head towards this other focal point. But once I hit the center of the lens, I'm going to go parallel to that. And that's going to give me the value that goes for that one. Then the third one I'm going to draw through the center of the lens. And if you look again, notice that those three are going to be off to the right. Where do they meet? They all meet on the left side of the lens. So I'm going to draw my dotted lines backwards. Notice that they meet there, and I get that point where they meet for that part. So nextly, we want to solve a problem. The image produced will be so many centimeters away from the lens. Notice that we're looking for our DI value there. And I can use, again, I have my focal length, I have my DO value. So I'm going to use 1 over di, 1 over do, 1 over f, and plug in my 40 and 25. Now notice that I put the negative in front of my focal point because diverging lenses have negative focal points. Or if you remember, I have my eye on this side of the lens looking through the lens because the focal point is on the other side than my eye. That's what makes that a negative value. Solving that, I'm going to do the negative 25 x to the negative 1 minus 40 x to the negative 1, and then flip my answer one more time, and I get that negative 15.4 centimeters. Remember, what does that negative tell you? It tells you that it is a virtual image. So because I have the dotted lines touching the image there, that's got to be a virtual image. So B, the magnification of the object is going to be so many times. So I'm looking for the M value here, which means that I'm going to do my hi-ho negative dido equation. Negative 15.4 over 40, and I get a positive 0.385. Now, what does that positive tell you? Remember, it tells you that it's an upright image, which our picture shows that it is. And then the 0.4 roughly says that it's about 40% of the original value. And you can tell that that's a little less than half of the original value. Now, lastly, the height of the image is going to be, so I'm looking for HI in that case. So I'm going to take that other part of the hi-ho dido equation, put in my magnification, put in my HI is what I'm solving for, and then 8 centimeters was the object height originally. And I can solve and say my new object height is this 3.08 centimeters. And that is a diverging sample problem. So in summary, you'll notice that we're still doing real or virtual, upright or inverted, small or larger. We still have our 3 ray rules that we're drawing. You really only need 2 of them to get a good picture, but the third one helps confirm where it's at. And they're more or less the same as the mirrors. So parallel, focal, focal, parallel, and then through the center. But the biggest thing to remember is that there are always 2 focal points, and you only use each one once. Only use each once for that. So then we have our converging lens, which is also known as a double convex. Convex because it has this bowed out. Converging because it pulls using my fingers on the screen, because it pulls the light rays together on the one side or converges them on the one side. Or you have a diverging lens or double concave. So concave because it has those bowed in parts, or the concave parts. And then, or diverging because it spreads the light out as it's going through the image away from the focal point on the left. And that, in a nutshell, is a very quick review or a very quick topic of optics and dealing with converging and diverging lenses.